Welcome to our complete lecture on the bivariate simple regressions. This is the first of a two-part lecture series. There is assumption that you have watched simple statistics videos suggested in the second week of the lectures, and you have watched a video of me teaching on Introduction to Regression Analysis. If so, then we are good to go. For the sake of continuity, we will follow on from the sales and advertising expenditures example from the video Introductions to Regression Analysis and the lecture notes. Now, the first concept we are going to discuss is the population regression. Recall that the population includes every observation possible. So in this example, the population is all the travel agencies in the Tampa area. Now recall that a sample regression was a line of best fit for the sample of firms managers were surveyed, while the population regression line is simply the line of best fit using every firm in the population. Suppose we plot every firm data in the entire population. Sales and advertising expenditures are on the scatter graph. This means all firms in the entire Tampa area. The line of best fit for the population is our population regression line. So the population regression line is a regression line using the entire population of observations. The regression line denoted as follows. Beta 0 is the intercept term and beta 1 is a slope coefficient. I'd like to now talk about the distinction between the dependent and independent variable. The dependent variable is a variable whose values depend on the other variable. In contrast, the independent variable is a variable whose values are independent or do not depend on the other variable. So you as a forecaster will have to think of the logic behind the relationship you are testing and see which variable is likely to depend on the other and which variable moves independently of the other. Okay, let's try to figure this out for our sales and advertising expenditures example. Now, is it plausible for causality to run from advertising to sales? Well, it seems to make sense, right? The more money spent on advertising, the higher the expected sales. Let's see if causality runs the other way. The more sales a firm has, the more the firm is willing to spend money on advertising. This to me does not make sense. If a firm has high sales, why would this firm like to spend money on advertising? Sales are a dependent variable as its values change according to advertising expenditures, and advertising expenditures are the independent variable as its values are independent to changes in sales. When setting up the regression equation, the dependent variable is always on the left side of the regression equation, and the independent variable is on the right side of the regression equation. When displaying our data points and regression line on the scatter graph, the dependent variable is on the y-axis and the independent variable is on the x-axis. So in our example, sales is on the y-axis and the independent variable, which is advertising expenditures, is on the x-axis. Depending on the textbook, the dependent variable can also be referred to as regressant, endogenous, or response variable. The independent variable can also be referred to as regressor, exogenous, or explanatory variable. Suppose we have the following population regression line. Now recall that the population is assumed to be unobservable as it's infinitely large and it's too costly or time-consuming for us to go out and survey all firms in the Tampa area. So in fact, this population regression line is unobservable. However, we can estimate the population regression line with our sample regression line. That is, we take a random sample of firms from the population, say 7 firms, and record sales and advertising expenditure values and estimate the sample regression. If the sample is large enough and if the observations are randomly selected, then the sample regression line should be a good approximation of the population regression line. This is similar to how in assignment 2 we use the sample mean as an approximation of the population mean. The population regression is a true relation between sales and advertising expenditures, whereas the sample regression is only a sample estimate of that relationship. The sample regression line is denoted as sales equals to beta hat 0 plus beta hat 1 times advertising expenditures. The hat on top of the betas tells us that they are estimates of the population betas, or the sample regression line could also look like this. Here, the little b's are estimates of the population betas. How the sample regression line is written depends on the textbook. I will use lowercase b's for estimates in order to be consistent with the notation in your textbook. The main thing to remember is that The population regression line is not observable as we need all observations into entire population to calculate it. However, the population regression line is a true relationship between your dependent and independent variable, and the sample regression line is observable as we calculate it using our sample of observations. It is used as our estimate of the population regression line. The population is infinitely large, and we are interested in the population mean. However, the population mean is not observable as we could not observe the entire population. So what we will do? Well, we will take a random sample from the population and calculate the sample mean. And using the sample mean, we will make estimates or inferences about the population mean. Now, in terms of regressions, we cannot observe the population regression, but we can observe the sample regression. And so we have an estimate and can make inferences on the population regression line. How do we make inferences again? Good old hypothesis testing. Time for a quick refresher on residuals. Suppose we have our scatter graph of our sample of respondents and we fit a sample regression line. Now suppose a sample regression equation is as follows. Let's make a prediction. For one of our respondents, Sally, who is the manager of firm K, she spent $3,000 on advertising. Based on that regression line, this firm is expected to have $25,000 of sales. How did we figure this out? Simple. We substitute $3,000 for advertising expenditures. So 10,000 plus 5 times 3,000 equals to $25,000. However, firm K's actual sales lies above our prediction. The firm actually have $28,000 of sales. This error in our regression model is known as a residual. It's calculated as the actual sales minus the predicted sales. This hat here means it's a prediction. So firm's K residual is 28,000 minus 25,000, which is $3,000. Perhaps firm K has an excellent customer service. Now suppose Peter, who is the manager of firm G, spent $5,000 on advertising. Based on our regression model, the firm is expected to have $35,000 of sales. However, this firm's actual sales in the dataset is $25,000. So the residual is equal to minus $10,000. Perhaps this firm has no innovative travel packages and actual sales are less than was predicted by the model. The sample regression equation can be written like this, where epsilon hat, a Greek symbol, represents the residuals. The residuals contain other factors that affect sales but are not included in the model. This may include factors such as customer service, travel packages, destinations, location of the travel agency, and so on. I'd like to now introduce the error term. Suppose we have the entire population on the graph, and let's imagine the population regression line. I say imagine because in reality the population regression line is not observable. Similar to residual, the error term is the difference between the actual sales and the population regression line. However, since the population regression is unobservable, then so the error term. This is because the error term is calculated using the population regression line. The error term informs us to how well the regression explains the data. Large error terms mean that the model isn't that great at explaining the data and making predictions, and small error terms mean that it's a good model, it makes accurate predictions. But we can't observe the error terms. No worries, we will use residuals as estimates of the error terms, just like how we use the sample mean as an estimate of the population mean. Later in this lecture, I will introduce a measure called R-squared statistics. This statistics uses the residuals of the sample regression model and tells us exactly how well the model explains the data. The error term is often denoted as mu or epsilon. The residuals are denoted as mu hat or epsilon hat or E in our lectures and our textbook. We will use E, so E is an estimate of mu or epsilon. Always remember that hats mean that these are the sample estimates, so from now on we will use epsilon when referring to the error term, and the residual will be expressed as mu hat or E. The best way to learn regressions is through an example question. You survey 7 random managers and record down the current advertising expenditures and sales. You estimate a simple regression line, and the output is as follows. This Excel output is easier for some of you, but is not as hard as it looks. We are going to break this down into little pieces as we work through in this example. What is the sample regression line? If firm H is planning to spend $7,000 on advertising expenditures, what are expected sales? Is there a statistically significant relationship between sales and advertising expenditures? So let's start with part A. What is a sample regression line? First, we are dealing with a sample regression because we are conducting this analysis on a sample of 7 randomly selected managers. Recall that the sample regression equation looks like this. The B coefficients instead of betas, since these are the estimates of the true population coefficients. The sample regression line is the estimate of the population regression line. This B0 is the intercept term and refers to the point at which of the sample regression line intercepts the y-axis. A high value for beta 0 looks like this, and the small beta 0 looks like this. Beta 1 refers to the slope of the sample regression line, and if you recall from high school, the slope is rise over run. A large positive value of beta 1 would make the regression line look like this, as the slope of the line is steeper, and the small beta 1 value will look like this. Regression line is flatter. A negative B1 produces a downward sloping line. So back to the question. What is a sample regression line? Well, basically this question is asking us to write B0 and B1. Let's look at the regression output table again. The section of the table that contains up to beta 0 coefficients is here. More specifically, these values here under the label coefficients. The first term is beta 0, that is why it says intercept here. The second term is beta 1, its label says advertising expenditures. This is because advertising expenditures is the x variable in the regression equation, so B1 is a slope or the effect of advertising expenditures on the y variable. Substituting these estimated values in the sample regression equation gives us this. This is the estimated line of best fit is calculated by Excel for the 7 data points. In our sample, if firm H is planning to spend $7,000 on advertising expenditures, what is your prediction of this firm's sales? Well, first we have to write down the estimated regression line as we did in part A. This tells us how to make predictions for sales based on some firm's advertising expenditures level. All we have to do is insert the firm's spending level here and calculate the value for sales. So in this firm's case, we substitute $7,000 for advertising expenditures and the firm's estimated sales is 46,363.03. So based on firm's level of advertising expenditures, we predict the sales to be close to $46,363. This is what we expect given the information we have. Part C. Is there a statistically significant relationship between sales and advertising expenditures? Well, we have to ask ourselves what would the population regression line look like if there was no relationship between sales and advertising expenditures. If we draw the regression line and there is a positive relationship between sales and advertising expenditures, it should look like this and have a positive slope coefficient. If there is a negative relationship, it should look like this with a negative slope coefficient. So if there is no relationship between sales and advertising expenditures, the regression line should be flat and the slope of the regression line, which is rise over run, will look like this. So when there is no relationship, the slope coefficient B1 is equal to 0. So what we have to do now is to use hypothesis testing to determine if the population regression slope coefficient is equal to 0 based on what we observe from the sample regression line. Record that we should use a statistical significance level of 5% unless otherwise stated. Let's go back to our Excel regression output. You can see here that we have for each coefficient estimate, standard errors, t-statistics, and p-values. This should look familiar. In fact, they should remind you of hypothesis testing. But what are we testing? What is the null hypothesis and what is the alternative hypothesis? By default, all statistics software packages conduct the following hypothesis test on the regression coefficient. The sample slope coefficient B1 is equal to 0. This means there is no relationship between sales and advertising expenditures, and so the true population regression line is horizontal like this. Or that B1 is not equal to 0. This means there is a relationship between sales and advertising expenditures. So for example, the true population regression line that might look like this. Okay, So looking at output, specifically looking at the advertising expenditures, this relates to the coefficient of beta 1, which is the slope of the regression line. This will tell us whether there is a relationship or not between sales and advertising expenditures. By default, statistical software packages conduct this hypothesis test whether the B1 coefficient is equal to 0 or not equal to 0. That is, whether there is a relationship between X and Y in the population. Now, don't worry, all the hard work in solving this hypothesis test has been done for you by Excel. All we have to do is look at the corresponding p-value. Now recall from your hypothesis testing lectures in Chapter 2. If the p-value is higher than your significance level, or alpha, we do not reject the null hypothesis. If the p-value is smaller than alpha, we do reject the null hypothesis. Looking at the table, we see that the p-value for B1 is this number here, 0.009951, pretty much smaller than 0.05. Recall that the significance level for this equation is 5%, so the p-value is smaller than alpha, 5%, and we reject the null hypothesis. The null hypothesis states that there is no relationship between sales and advertising expenditures. Therefore, we reject the null hypothesis and conclude that there is a statistically significant relationship at the 5% level. This means that the more a firm spends on advertising on average, the higher the sales are for this firm. What do we mean by a statistically significant relationship? You'll hear this a lot when dealing with regressions. In short, it means that there is a true, causal relationship between X and Y. It is not simply due to sampling variation or sampling error. It's a true relationship between X and Y. Now, to fully understand what I mean, we need to discuss the standard error of P. Some of you may recall the standard error on hypothesis testing. The standard error in regression analysis is very similar to that in hypothesis testing. Let me explain. Recall that we are using a sample of observations. Why? Because the population is too large, but what is the drawback of using a sample? Well, there might be sampling variation. That is, a sample may not perfectly reflect the population due to noise or randomness in the sample selection process. Suppose we have the following population regression line. It is a dotted line as it's unobservable, but let's assume for now that we can observe. Now imagine you grab a random sample of individuals and estimate the following regression line. It's pretty close to population line. Suppose we draw another random sample from the population and estimate the second sample regression line. Now, all the sample regression lines were very close together. In fact, they are all very close to the population regression line. Thus, there are good estimates of the population regression. In this case, the sample B estimates has a low standard error. It is a measure of how consistent the sample B's would be if we resampled over and over again. It's a measure of the amount of sampling variation when estimating B. Now suppose instead the sample regression looked like this. You can see that in this case the sample regressions are not similar at all. There is a high level of sampling variation and the B estimates differ markedly from one sample to the other, so there is a high standard error of B. In this case, the standard error of a coefficient tells us how much sampling variation there is if we were to resample and re-estimate B. It's an indication of how reliable the sample estimates are in our sample regression output. Suppose we estimate using our sample that the slope coefficient for sales and advertising expenditures is equal to 1. The question of statistical significance is this. Is 1 sufficiently large enough for us to conclude that this represents a true relationship between sales and advertising expenditures? Or is 1 too close to 0 and thus likely to be caused by sampling variation and randomness? Well, suppose the standard error is 0.2. In this case, an estimated beta of 1 is 5 standard errors away from 0, which means it's pretty far away from 0. This is evidence that the population beta is not equal to 0, and that there is a real relationship between sales and advertising expenditures. However, suppose instead that the standard error is 2. Then b of 1 is only half a standard error away from 0. This means it's very close to 0. This is evidence that the b is likely to be 0 and that there is no real relationship between sales and advertising expenditures. You can see that standard error is vitally important in determining whether there is a true relationship between X and Y in the population, as it gives us a sense of how far our sample B estimates are from 0. How do we know for sure whether the number of standard errors away from 0 is large or small? That is, how many standard errors until we conclude that sample B is too close to 0? Well, we will use the critical value. It tells us the number of standard errors needed for a sample coefficient to be statistically significant, that is, for it to be statistically different from 0. Statistical review in Chapter 2 covered the critical value in the hypothesis testing lectures. Be sure to check it out if you are unsure about critical values. Statistically insignificant means that even though B is non-zero, its true population value is likely to be 0.